right, so today we have Kaiwen Sun give the first Quiver meeting after the summer break, and he will tell us about the intermediate algebra 7.5. Take it away.
Thank you. I'd like to first thank Julius for the nice invitation to present my recent work. It's very nice to see many friends after Amiens. So this talk is about a very exotic algebra called E7.5. And this is based on a recent paper with Professor Kimyeong at Chaos and another number theorist, Haowu Wang in China. So I don't know how many audience heard about this E7.5 before. This algebra is not a simple or semi-simple algebra, but an intermediate algebra. So it was independently found in physics and mathematics. In physics, this was found by Mathur Muhki Sun in 1988 in the classification of 2D rational CFTs. And in mathematics, this was found by Deligne and Cohen and Wang in 1996 in representation theory. So some typical property of this algebra is it has dimension 190 and dual coset number 24.
I should make a comment here because you don't give justice to Cvitanovi because he did this work before Deligne and before Mathur and Muhki. So you should really give credit. Not for nothing, it's called Deligne-Cvitanovi, right?
Yes.
You should look at the work of Cvitanovi, and you will see that it was before, and it contained all of the lists. So I think he should receive the credit. And he's a physicist. So when you say in physics it was first found by Mathur Muhki, that's not correct.
Oh, really? I thought Cvitanovi found this exceptional series, but not E7.5 in his book. No?
Okay, the precise, this I don't know actually. So
yeah, of course, in the new version of his book, I think new version after like 2004, I think he also added this E7.5 in his in the new version of his book. But my impression is he also found this exceptional series, but not E7.5 itself.
7.5. I see. Okay, I'll ask him. Thank you.
Okay. Yeah, let's go on. So, okay. It's great to come to the Deligne-Cvitanovi exceptional series. So interestingly, the critical property of this E7.5 is that it fills a hole between E7 and E8 in the Deligne-Cvitanovi exceptional series. So the more information I will give you later. And although this E7.5 is not simple, but in many sense, it behaves like a simple algebra, just like other simple algebras in the this exceptional series. Right, so this is a basic profile. So of course, this is a Quiver meeting, and I'm supposed to say, how is this related to Quiver? So in my experience in Quiver gauge series, so not only the shape of the quiver matters, but also the co-marks of each node. For example, say in E7 quiver or affine E7 quiver, so we know that in each node the gauge group UN should be the n should be proportional to the co-marks. For example, this is E7 quiver, and here I marked every co-mark for each node, and I think this is familiar with the audience. And in particular, the dual coset number 18 of E7 is the summation of all co-marks plus the affine node co-mark 1. So in total, this is 18. So a natural question is, can we make sense of E7.5 quiver? So I can tell you the result first and leave the explanation later. So the E7.5 quiver has the same shape with E7, but interestingly, in these three nodes, you need to double the code marks. So these three nodes are special, which later we will call the fermionic fundamental weights. And you can see that it's 2, 3, 1. If you double these three code marks, and you will increase the dual code number by 6. So in the end, you got the dual code number 24 of E7.5. So the reason of this doubling, I will talk about it later. Okay, so I give you an outline of my talk. So first of all, I will review the history of how physicists and mathematicians found this E7.5. Then I will review you the two known results about E7.5, which is the so-called CFT or VOA or WDW model of E7.5 at level 1. So another one more recently is which I will call the rank 1 E7.5 instanton VOA. So this at level -5. So these are two known things involving E7.5. Then I'll go to the new results of ours. So first of all, we can give a construction of E7.5 at level 2. So and we will also discuss the very surprising properties at a higher level. That is a WDW model of E7.5 at higher integral levels. Then I will say another generalization, which is generalization from this rank 1 instanton VOA, which we will call rank 2 and higher E7.5 instanton VOAs. Then I go to a conjectural Weyl dimension formula for E7.5 representations. And in the end, I will say something about the possibility of E7.5 will serve as a gauge algebra. Okay, so so far, any questions? Okay, if not, let's go on. I will first tell you how physicists found E7.5. So this was found from the study of modular linear differential equations. So this was proposed by Iguchi and Ogri, and to classify 2D rational CFTs for a given number of characters. And the simplest case is to consider the second order holomorphic MLDE. This is also studied by number theorists. So this was also called canonical Zagia equation. So here D is the so-called third derivative defined by in this way. So the E2K is the Eisenstein series of weight 2K. There are some weight 2K modular forms of SL2Z, and so this third derivative raises the weight of modular form by 2, such that this equation makes sense. And mu is some constants. So here chi are the characters of 2D rational CFTs. So if we want the two solutions of this equation to describe the characters of 2D rational CFT, then we must have some requirements. So first of all, there is the vacuum character, which have an overall Q power depending on the central charge, and one is the unique vacuum. There are these Fourier coefficients should be non-negative integers because they count the states in CFT. And the non-vacuum character, so this H is the non-vacuum conformal weight. So it also should have the Fourier coefficients all as non-negative integers. And these conditions, by requiring these conditions, the nice finding of Muhki Sun is that there are only finite many possibilities for this constant mu, so which was also proved later in mathematics. So let me show you Muhki Sun's result. So this is the table I cut from their paper, and they found that there are only 10 possibilities, such that the CFT character satisfy that Kaneko-Lagia equation. So among which the first one is the familiar Liang model, which is the minimal model 5,2. More precisely, this is the so-called the effective theory or the Galois shuffle of Liang model, which I will mention later also. And there are other 8 possibilities, which are exactly the WDW models of gauge group G belongs to the Deligne-Cvitanovi exceptional series at level 1. And you see that they found the 10th, there is one more possibility here. So they found that the solution also satisfied by the requirement of CFT characters. So this guy have here M1 is the so-called spin 1 current. So for WDW models, they are the dimension of the Lie algebra. So you can see that this guy has a central charge 38/5 and a non-vacuum component weight of 4/5 and a dimension 190. So of course, they found that there is no simple or semi-simple WDW models satisfy this requirement. So they gave a question mark. And in the paper, they wrote a paragraph to comment this puzzle. So you can see that this is also a cut from their paper. They said that we do not know a theory satisfies the property given in the table, which are the 2 characters. But they found that many of the central charge weight are consistent fusion rules. There is fusion rules. And in the end, they said that it thus seems quite plausible that there exists a 2D rational confield theory corresponding to this rule, based on some yet unknown symmetry algebra. And nowadays, we know that this symmetry algebra is just the E7.5, and this CFT is the WDW model of E7.5 at level 1. In fact, a simple understanding of this is a coset construction, which is E8 level 1, coset the effective Liang model, which is the first row I just mentioned. Right, so this is how physicists found E7.5. Now let me tell you how mathematicians found E7.5. So first of all, so for example, in Deligne's paper, short paper in 1996, he found that this series of exceptional Lie algebras, simple Lie algebras, have some remarkable properties in representation theory. For example, one of the formula he found is that the dimension of this simple Lie algebras can be written as the rational function of the Dioukos number. For example, this is a beautiful formula. And in fact, many other representations can also be written. The dimension of some other representations can also be written as some uniform formulas of the as rational functions of Dioukos number, and every factor is linear. And so in the same year, so these 2 mathematicians, Cohen and Wang, they did a huge amount of computations, and they found in total 25 such kind of dimension formulas. So these are called Deligne dimension formulas nowadays. And later, Landsberg and Manive, so another 2 mathematicians, they even proved a formula for arbitrary so k theta representation. So here theta is the highest root, and k theta, which serves as the highest weight of the representation. And in all these dimension formulas, they noticed that if you put a Dioukos number 24 there, you always get an integer. And this phenomenon is remarkable. For example, if you put Dioukos number 24 here, you will get 190. If you put 24 here, you get a 15504. And this phenomenon is unique that if you put any other integer coset number in this dimension formulas, so except 24, you will not always get integers. So this remarkable phenomenon inspires mathematicians to propose that there indeed exists algebraic structure there, so which is called intermediate Lie algebra. So this intermediate Lie algebra filling the hole between E7 and E8. This was later proved by Landsberg and Manive. And we can think or define this algebra as a subalgebra of E8 while containing E7 algebra, E7 Lie algebra, where its adjoint representation can be decomposed as E7 representations in this way. So we know that the adjoint representation of E8 is 248. In fact, it can be decomposed to E7 half representations in this way. So here, this 57 serves as a fundamental representation of E7 half, similar with the 56 serve as the fundamental representation of E7. So yes.
The 57 fits into some dimension formula, but you only showed the formula which involves the highest root. But
yes, 57 was also appeared in Cohen domain's prediction.
I see. Okay, so did they manage to find the 7-parameter family for the dimension formula?
No, this is not even done today.
I see. Okay, so what's the best thing known today?
Well, best thing that I know as we can in our paper this year we predicted we can predict infinite many representation dimensions, but not all representations.
I see. Okay, thank you.
Right. So I should say that this concept of intermediate algebra is not new. In fact, this Steppin, he studied this for like 3 decades or so. He wrote like 5 papers about this ABCD type intermediate algebra. But it seems this E7 he didn't consider this E7 and E7 does not fall into the pattern of his study on the classical types. Right, just to mention this Steppin's works. Right. Okay, now I explain to you how physicists...
Sorry, I also have a quick question.
Please.
Is there a precise definition of an intermediate algebra? Or like a simple definition?
Simple definition.
I mean, I can see what is meant by intermediate algebra. Is there like is it a defined thing or?
Well, I would say there is no uniform definition.
Okay. Yeah, that was my question. Good.
Yeah,
all right.
just case by case, because this phenomenon is very special. Because, for example, you don't have E6 plus half, that kind of thing.
Yeah, exactly. Okay.
Yeah, E6 plus half does not exist. Yes. Okay. Right. Now let me tell you more details about this WEW model. E7 half at level 1. So as I mentioned, this guy has central charge 38/5 and 2 conformal primaries with weight 0 and 4/5. So of course this was found by Muhki Sun and later more rigorously by this Japanese number series. So in this case, in fact, here I show you the 2 characters. So like this. And they are the solutions of this second order MLDE. And you can recognize this 190 as the adjoint representation dimension and 57 as the fundamental representation dimension. So in fact, this VOA was later also constructed by a VOA expert, Japanese VOA expert Kawasetsu.
So a question.
Yes.
Can you say what was the contribution of the Japanese group over the work of the Indians?
Well, almost repeat their work, but to be honest, I don't know what. Yeah, maybe
so,
write in mathematics language.
I see. Okay, so
yeah,
it's difficult.
I have the same puzzle with you.
I see. Okay. Okay.
Yes. So yes. So one nice coset construction given by Kawasetsu is that he found this E7.5 at level 1 can be realized by this E7 level 1, but by coset with a minimal model M5,3. Yeah, this can also be realized by the product with effective minimal model 5,3. Right. So
is this notation, is it one of the minimal models of BPZ?
Yes. So you see E7.5 has a central charge 7. So minimal model 5,3 has central charge negative 3/5. So in total it's 38/5. But on the other hand, the effective minimal model, this guy has a positive 3/5.
I see.
Yes. Right.
Okay.
Okay. So let me tell you something new after this MLDE approach and coset. So that this is Harvey and Wu discovered in 2018. So where they defined this, they found a new the definition of helicopter for the vector valued model forms of weight 0, and among which a very good example they found is that if you act this T19 Hack operator, which was defined by them on the Li-Yang model characters, you will exactly get the 2 characters of E7.5 at level 1. So this Hack operator TP they defined can map the central charge by multiple P and a conformal weight by multiple P, but then modulo Z. So you can see that this times 19 gives this central charge, and this conformal weight times 19, but modulo Z gives you this non-vacuum conformal weight 4/5. And one consequence is that the characters of E7.5 level 1 should be written as a homogeneous degree 19 polynomial of the 2 Li-Yang characters, which are well known to be the Rogers-Lagrangian equations functions. So phi1 and phi2 like this. So we can have a compact formula of the vacuum character of the E7.5 level 1. And now let's turn to another sort of known VOA associated with E7.5. So this goes to the for the RCFT VOA correspondence by Rastali and Merlin collaborators. So among which a series of familiar examples are this for the equal to instanton RCFTs, so which often denoted as HG. And for example, so it was classified that this G can be A1, A2, D4, E6, E7, E8. So notice that there is no G2 and F4 here. And this correspondence on a quantity level says that the correspondence to VOA is this G at level dual cosine number over 6 minus 1, and the conjecture says that one consequence of the conjecture is that the Schur index of the 4D RCFTs is equal to the VOA vacuum characters. So this was more rigorously studied later by Arakawa and Kawasetsu. And they also proved that these VOAs are quasi-Lisi and the vacuum character satisfy a uniform second-order MLDE. Of course, I think this was also found by Rosselli and collaborators. But in this paper, they proved this. For example, if we set this G as E7.5 by hand, then this level should be -5. And the second order MLDE is like this. And if you solve this, you get this vacuum character. So in fact, in this paper of our Kawasetsu, in the last paragraph, they mentioned this E7.5. So I just contributed this case to them. And one thing to be careful is that this second order MLDE, the second solution is not the rational, not the previous Q series solution, like the level 1 case, but a log solution. For example, so even in this case, the vacuum character also have a very good compact formulas. So also found by Japanese mathematicians. And so based on some representation we found in our current work, we can also decompose this vacuum character to the flavor character, which means all the free coefficients can be decomposed as E7.5 irreducible representations. And just a word that the second solution is the log 1. So like this, you can see that it's different from the level 1 MLD studied by Muhki Sun. Right, so I now will go to a higher level. So any questions so far? Okay, so how to define this WDW models for E7.5 at higher level? It seems for the past more than three decades, people didn't know or didn't think how to define this E7.5 at level 2. So we have some hint how to define this or the requirements. So first of all, we see that at a level 1 case, so this central charge formula still hold, and we just assume that or we hope that at least for small levels, this central charge formula for WDW models still hold, and this is the well-known formula for the conformal widths, where you have the quadratic Casimir of the representation. And if we assume this formula hold, then, for example, in the level 1 case, we will know that the fundamental representation will have quadratic Casimir as 40. So one tricky thing is that for simple algebra, this quadratic Casimir is defined by this bilinear form of the highest width times 2 rho. Rho is a Weyl vector, and with highest width itself. But sadly, this for E7.5, you can find that this is no longer correct. So this makes this question very tricky, and so just by these formulas, you will not know how to define it for higher level.
But does there exist a Weyl vector for E7.5?
Yes, that I will talk about later. But the problem is that even you define the Weyl vector for E7.5, this still does not give you the correct quadratic Casimir. For example, after I will introduce the Weyl vector for E7.5, but when you compute this guy directly, you won't get a 40 for this representation. Yeah, I will explain to you. This is a very delicate point. I think the main point is that for E7.5, we couldn't find a good bilinear form.
I see.
Okay, right. So then how we define this E7.5 at level 2? So this actually we found this by accident. So last year I was studying this Hecke operators with Zhihao Duan and Kimyeong Li. So we computed basically hundreds of examples. So we studied Hecke operator act on some small central charge CFTs characters, and we computed all these TP Hecke images to see how the characters look like. So among which one example is we consider this minimal model M13,2, and if we act T19 Hecke operator on it, then we will get a vector value model form of 6 components, and we found many evidence that that Hecke image should describe the E7.5 at level 2 characters. So I will show you the character later. But let's first see that this T19 Hecke image first maps the central charge by a multiple of 19. So this is exactly required by the central charge formula for E7.5 at level 2. And in the on the other hand, all the conformal weights. So these are the conformal weights of M13,2. So by Hecke operator, it gives this conformal weights. And let me show you this just by direct computation. So apply the Hecke operator T19 on the M13,2 characters. You will get this vector valued modular forms. So you can see that we have many evidence that first of all the Fourier coefficients are non-negative integers. Second, the vacuum character has the spin 1 current 190, which is exactly the dimension of E7.5. And then all other characters. So as we know that the leading Fourier coefficients should serve as a irreducible representation dimension of the algebra. And indeed, we found that all these numbers, besides this is fundamental representation, this is a joint representation. All these three numbers are also appeared in the dimension formula given by Cohen domain. If you put number 24 there, and we also have some. We also can show that this conformal weights will give the correct quadratic Casimir we need. All 6 characters gives the correct quadratic Casimir we need. So all this evidence is support us to believe that this indeed describes E7.5 at level 2. And we.
Do you know the Dinkin labels of?
Yes, I will get there.
Okay.
Yes. And you can also find that the 6 characters satisfy a 6th order holomorphic MLDE like this way. So we even computed the S matrix and the fusion rules, everything in our paper last year. And now
how can you tell the order of the differential equation?
Yes, normally if there are 6 components, then MLDE is the 6th order.
I see. Okay. Mm-hmm. Okay.
Right. So this year we found something even better. So we even give coset constructions for this E7.5 at level 2. So in this sense, if we can find these coset constructions, we basically can say that we did construct this WAW model of E7.5 at level 2. So in fact, these 2 cosets are very good, and they are somewhat similar with the so-called Maverick cosets found in 1990s. So for example, these are the Marbury cosets for E7. So interestingly, so I should note that this coset was actually found also found in an unpublished draft of Arakawa Kurtizik Kawasetsu, and also this coset. There is a previous paper by Miranda Chen, Gano, and Lockhart. They computed the central charge of this side, and they noticed that that central charge is the same with the central charge of M13,10. Now, of course, previously they don't know the characters, so they couldn't confirm this cosets. But now with this characters we found, we can really construct this coset and confirm that this side should be the so-called D6, A12 non-diagonal modular environments of M13,10. Okay, so I think this cosets I will just quickly show you. So the coset, basically we can even confirm the character identities for these cosets. So it's something like this. Okay, I'll go very quickly here. So another coset is so this involves a non-diagonal modular environments of M13,10. So you are familiar with the differential CFT bulk, then yeah, so these are their name for the modular environments, and you can check that. We checked that the character relations for this coset. So to say, we confirm this coset constructions. Right. So now let's go to higher level. So higher level.
Can I ask a question on the previous
Yes.
thing? So you have this, for instance, the 6 characters.
Yes.
You say they form a vector-valued modular form. So what's the subgroup of SL2Z which is left invariant? Is it some congruent subgroup?
So the vector-valued modular form itself is for SL2Z, but each component is for gamma 156.
Okay,
Yeah.
so it's
a subgroup of level 156.
Okay. So it's really okay. So that the index of that group would be really huge, but then there is a small vector-valued modular form. So it has only 6 components. Okay. That's what I wanted to know.
Okay. Yeah. Thanks for asking. So now let's go to higher level. So higher level is more difficult, and we didn't find such good thing as a hack image, but luckily we have some further hint. That is, in level 1 and level 2, we noticed that both E7.5 and E7 at level 1 and 2, they both have the same number of characters. That is level 1. They two both have 2 characters. Level 2, they two both have 6 characters. So we just assume, or we conjecture that, or we hope that at least for small levels, they two should have the same number of characters. Of course, this is a bold conjecture, but we later found many supports for this conjecture. And for example, for E7 level K, it's well known that number of characters are generated by this generating series. So for example, level 2 you have 6 characters. Level 3 you should have 12 characters. And this in fact is equivalent to say that all the irreducible representations of E7.5, at least for small levels, should be marked by E7 Duncan labels. And this is also why in the beginning I show you the quiver shape of these two guys are the same. Right. Of course, I need to explain to you the doubling of the co-marks. So now let me explain to you. So this we need to define the Weyl vector for E7.5. So remember the joint representation of E7.5 is 190. It decomposed to E7 representations by a joint plus fundamental plus 1. And so this inspires us to directly define this Weyl vector for E7.5 by taking half of the positive roots of E7 here and half of the 56 weights. And you need to be careful what half of the 56 weights to take. In fact, we chose the half of the width of 56 that has the positive intersection with the Weyl vector of E7. And by explicit computation, we found that, of course, we know that for E7 Weyl vector in the fundamental weight basis is all 1. And you just sum over 28 fundamental weights of, 28 weights of fundamental representation, you will get this number. And together, you will get the Weyl vector for E7.5 as this guy. So this means you can see that these 4, 6, and 7 positions are distinguished. So we call these 3 positions as the fermionic fundamental weights. So now I want to explain you this doubling. So if you want to regard E7.5 as a simple algebra, then you still want all these numbers to be 1. That means that for these 3 positions, you need to double the fundamental weights. So in the meantime, the co-roots are orthogonal with the fundamental weights. Then the co-roots will half, and then in the definition of co-marks, co-marks are defined with so associated with the co-roots. So if these 3 co-roots half, then that 3 co-marks should double. So this is why in the beginning, that 3 positions, this 4, 6, 7 positions, the co-marks double. And it's worth to point out that with this Weyl vector, so the very famous Friedenthal various strange formula for simple algebras still hold. So in this sense, it's still like a simple algebra. Right. So now let's go to the important thing, that is how to define the conformal width, which is equivalent to say how to define the quadratic Casimir. And in fact, for level 1 and 2, we already know the quadratic Casimir from the Heck images, Heck operator, and we found a formula, a very nice formula that is, of course, is a conjectural formula. That is, as I mentioned, so here, even you replace this Weyl vector as the E7.5 Weyl vector, then this bilinear form still does not always give you the correct quadratic Casimir. We found that as long as the fermionic fundamental weights are involved, you will need a correction. So we call this term as this odd term. And we conjecture this formula to reproduce all the correct level 1, the 2 quadratic Casimir. And it's actually, this correction is quite simple. So it's like these 3 positions are like fermions. So if they 2 met together, you will need a correction by half, or same fermions by half, or different fermions by minus half. But in the end, this formula, we found many evidence that this formula correctly describes the quadratic Casimir at least up to level 5. Right. So now let me show you this Dunking diagrams and representations. So these are some representation I collect. So you see that these are the representations whose highest weight is the fundamental weight. So of course, this number, I think the audience are familiar with E7 representations. So these are all E7 representations. So in the meantime, you can see that for each representation here, so all these numbers, in fact, already can be predicted by Cohen-Demann's dimension formula. If you put dual cos number 24 there, you can see that each of these dimensions a little bigger than the E7 representations. So so here it's also, so for each representation, the highest weight is this fundamental weight. Okay, you can recognize the adjoint representation of E7.5 fundamental representations and all these other representations. Right, so now let me tell you how we manage to study the structure for arbitrary level. So this comes the so-called MLDE approach we used, so modular linear differential equations. So one important, so in MLDE, not only the degree of the equation matters, but there's another very important index called index L, so which measures how meromorphic this MLDE is. That is the leading, the highest degree differential. The coefficients is weight 2L SL to the modular form. We know that holomorphic modular form, the weight must be even. So all the L should be integer, should be non-negative integers. And this also was developed by Mathur, Muhki, Sun. So they found that if a degree D component vector value modular form of weight 0 satisfy this degree D MLDE, then by analysis they found that the exponents of the components Q series, which in CFT case just equal to this well-known combination, is related to the index L in this simple formula. So now, because we have assumed that the component width is proportional to the quadratic Casimir, and we also have a concrete formula, a conjectural formula for the quadratic Casimir, then we can actually compute this index L for arbitrary level, so we just compute in this way, and we found that for E7 and E7.5, for level 1, 2, 3, 4, 5, their index is the same. So index 0 means holomorphic MLDE, which means the highest degree differential, the coefficient is constant, as I showed you previously. But from degree 3, it's no longer holomorphic MLDE, but meromorphic MLDE. The important thing is these numbers must be integers, as required by basic property of modular form. But if we continue to compute this level, so amusing things happen. So we know, because you can see that from level 6, so E7, this index of MLDE is still integer, but for E7.5, this begins to be fractional, which contradicts with the basic fact that the MLDE should only can have integer index. So this means that if you put it into the CFT or VOA language, this means that for E7.5 at a level higher than 5, this cannot be rational. So this arises with our surprising conjecture. Actually, one of our main results that WAW model E7.5 at level K is only rational for level 1, 2, 3, 4, 5, no higher. And as a comparison, so the familiar WEW models we know that for any simple Lie algebra and any positive integer level k is always rational. So this is a very surprising phenomenon for the VOA community. In fact, they also recognize something from the viewpoint of W algebra. Right. Okay. So this is the positive level cases. And any question? Okay. If not, let's have a brief look at the higher instanton case. So this originated from a very good work, a great work of Russellian collaborators, which started this rank 2 HG series, the VOAs. They found that, here should be the Deligne-Cvitanovi exceptional series. And they found that if we turn off the SU2, there is an actual, for rank higher than 1, there is one more SU2 fugacity. So if you turn off that, and then the Schur index of this rank 2 for the RCFTs satisfy so-called twisted fourth order MLDE. This is the equation found in Russelli's paper. And we found that if you put a Duke number 24 here, you will have a perfect solution like this. And in fact, all these numbers, we further decompose this to the representations of E7.5. So these are which we call flavored vacuum character. And we can we even turn on the SU2 fugacity back. So this suggests us to believe that there should exist a good VOA with this vacuum character, and even in the rank 2 case. So which with a level, if it's rank n, then the level is minus 5n. There is an actual SU2 factor, also with negative level. Okay, so I think the Weyl dimension, this is the Weyl dimensional formula. I can tell you the basic conclusion is that you can see that this is a direct generalization of Weyl dimension formula, where you just enlarge the set of all possible roots. It's very similar with the definition of the Weyl vector. And importantly, this generalization of Weyl dimension formula only work for the what we call the purely bosonic widths. That means that there is no fermionic width, that these 3 positions must be 0. If you turn on these 3 positions, then this formula will not give you an integer number. So in fact, this formula, of course, from this formula, you can get an infinite number of dimension of representations. Many dimensions are predicted by Cohen domain, so we can cross-check. I found the perfect agreement. And
extra over. So you said you have more.
Yes, of course. They only found 25 dimensions. So
20 presentations? Or?
Yeah, they only found 25 dimension formulas. So if you put 24 there, you get 25 dimensions. And then Landsberg and Manive, they proved this case where N1 is arbitrary, but all others are 0. In fact, this is I'm just going to say that Landsberg and Manive proved this N theta representation. Theta has the root N arbitrary. That means our formula to set N2, N3, N5 at 0. Of course, this our formula is give the same answer with Landsberg and Manive. And we also found a second Weyl division formula which allows us to turn on 1 fermionic fundamental weight, which means that these three positions.
Wait, before going back to the previous page, do you have a dimension formula which depends on 4 labels, N1 and N5?
These 4 labels are arbitrary.
But do you have a dimension formula which depends on 4 parameters?
Yes, this formula is depends on 4 parameters.
I see. So you're saying this dimension formula satisfies all of those infinitely many. I see. Okay, thank you.
Yeah. So I'm saying that we did further. So we have the second Weyl dimension formulas, which allows us to turn on these 3 positions as 1. So one of these 3 positions can be 1. Then these 4 positions are still arbitrary. So when there is a fermionic fundamental width, things becomes very complicated. That is what I mean. We couldn't turn on all these 3 positions. We can only turn on 1 here so far. Right. Yes, now let me show you the dimensions for small levels. For example, this is the level less than 3. Of course, our dimensions cross-check with everything. So those things predicted by Cohen domain. So I have marked their Cohen domain's notation here. So these are their notation. As I said, they have 25 dimension formulas. You can see that some dimensions they couldn't predict. This side is E7, this side is 7.5. This is level 4. You can see began from level 4, there is already some dimensions we couldn't predict. Right. Okay, so this is the last page. So I just want to briefly mention this possibility of gauge algebra. So this is very formal, and so yeah, I like this formula for Ami has previous very nice formula for the Wang instanton Hilbert series. So here yeah, so which is okay, Wang instanton Nekrasov partition function can be expressed by this infinite summation, where this V is exponential epsilon plus. And these are the characters of n theta. And theta still is the highest root. So because now for E7.5, we just put 24 here. And luckily, so we already know the dimension of these representations. As I mentioned, so this was even proved by Landsberg, Manive, by the mathematicians. And then we can do this infinite summation. And in the end, we get this rational function of V. And yeah, very nicely, this is palindromic with respect to V. So I think as was pointed out by Amihe to me in Amiens. So this is required by the Gorenstein property. So far, this is the observation I made, but of course, I still don't know how to turn on this E7.5 gauge scarcities in this Nekrasov partition function. And in the paper, we also even predicted some 60 series, where E7.5 serve as a 60 gauge algebra. So notably, this was new. So these are, if you are familiar with 60 RCFT, so these will be on the so-called -10 curve. So, and in the meantime, E7 series on -8 curve, E8 series on -12 curve. Okay, so about the possibility of as gauge algebra, so I only have this yeah, very preliminary support. Okay, I think my time is up. Yeah, thank you.
All right, let's thank Kaiwen. Do we have more questions?
So is Stefano still there?
Yes.
So you computed this function, right? The one we see now.
Yes.
You remember this, right? You did this, so we can check whether the numbers. Well, the numbers will of course agree, but we couldn't say much back then. It was a while back.
Yeah, I think the question was that in order to interpret it as some symplectic singularity or even as a modular space of a theory with 8 supercharges, you would expect to get the flavor symmetry to be a simple Lie algebra. I think that's what follows from physics and also in mathematics. I think Namikawa has a paper where basically proves math statement for that. So that was a question mark. In fact, if I may ask a question related to this,
Yes,
if you take
please.
the VOA for the E7.5 one instant homogeneous space, what is associated variety
What's
of that VOA?
type?
Can one count? Can one then get this Hilbert series?
I think this is not known, so I think you mean this level -5 case. So in Arakawa Kawasetsu's paper, they only mentioned this C7.5 in the last paragraph. So
Actually,
I wouldn't say this VOA is even constructed or something.
maybe Wenbin could say something useful about this.
Wenbin, yeah, I give a talk in his place this May. I don't think he knows how to construct it. Yeah, but he did say something about the G2 case somehow. He knows some for the RCFT associated G2 or something. But my previous knowledge is G2F4 and E7.5. There is only VOA, but no for the RCFT.
Yeah, so it seems like this comment that Stefano was saying is that the Hilbert series that you have over there is good for Gowenstein, but not for a symplectic singularity.
Yes, you're probably right.
Yeah, all modular spaces of instantons are symplectic singularities, and this one doesn't fit with the requirements, unless we misunderstand something.
I see.
Possibly a related comment is that, if I remember correctly, 57 is a nil radical of the adjoint of E7.5.
Yes.
So I wonder if that goes away when you go to the associated variety.
Yeah, 57 is a fermionic representation. It does not appear in of course does not appear here, right? But is this what you mean?
It says that you could impose it as a relation on quadratic numbers. Is that what you're saying? On quadratic Joseph relations, you said?
No, that's not what I said, but since this is a new radical, you could you could imagine that it's not there in an associated variety. So you see it in the Schur index, but not in the Hilbert series. That's what I'm wondering. That could fix the puzzle.
You mean the Namikawa puzzle?
No,
Yeah, or the physics puzzle.
Or the physics puzzle, yeah. I see.
But for Namikawa, you fail already at order t squared with the adjoint.
But if you take the variety, then you remove stuff that doesn't go to higher order. So it also wouldn't be that useful.
You want to remove stuff also from t squared, or what? I didn't get.
Yeah. So if you take but I think that's the point. That if you have not put an operator that carries some global symmetry, that's fine. But if you remove it, then it's gone. Like if you take the variety, then it's not there.
Mm-hmm.
Okay, very nice. Do we have more questions for Kaiwen?
Thank you for the good questions. Yeah, this is a very novel topic. Just the beginning, actually.
Very good, very good. Okay, let's thank Kaiwen one more time.
Thank you.
And we can go off the record.